Welcome back to the office. I want to take a look at subsets and subgroups. Now, previously we talked about binary operations. Use the right terminology, unlike the last video. Okay, binary operations. We talked about having an induced binary operation on a set. So this is going back into, I think, section 2, where we talked about binary operations. So if I have a binary operation on a set, wonderful. If I consider a subset where that binary operation still holds, or there's closure is the main thing, then I have the induced binary operation on that subset. And that's awesome. So if I want to extend that idea to groups to create a subgroup, essentially I only have to verify a couple of things. And we'll take a look at what we have to verify in a theorem a little bit later. But if it is the case that we have a subset of a group and that subset is closed under the binary operation, so it is an induced operation on H, if it happens to be that H is itself a group, then H is said to be a subgroup of G. So a subset, which is a group, is a subgroup, assuming that G was a group to start with, right? It's only a subgroup if G itself was a group. So we can write that as H. This looks like the less than or equal to symbol, and that's perfectly fine. H is a subgroup of G. Or H is a subgroup of G, just like we can talk about 3 is less than or equal to 4, and 4 is greater than or equal to 3. Both of these can be read as 3 is less than or equal to 4. So both of these would designate that we have H as a subgroup of G, H as a subgroup of G. Excellent. If we have H is a proper subset of G, then we can use that similar notation, remove the line underneath to recognize that it is a proper subset that is also a subgroup. Okay, so proper. So it's not actually equal to G. So let's take a look at a couple of examples of subgroups and not subgroups. One of the subgroups that I would like to take a look at is consider. So let's consider the group Z under addition. Excellent. So under addition, Z has identity 0. It's associative. It happens to be commutative, so it's an abelian group. Right? We have all these nice characteristics here. Notice that Z plus is not a subgroup of Z under addition. So Z plus is all of the positive integers, 1, 2, 3, 4, and so on. Well, if I'm using Z plus, all of the positive integers, then we have a couple of problems. We still have associativity. That's wonderful. All right, that's just kind of inherited from Z itself. But we also need to have identity and we need to have inverses in order for us to actually have what we're looking for. We also need closure, right? We need that closure aspect. However, 0 does not belong to Z plus. So there is no identity element. Identity element. And Z plus is not a subgroup. So here I'm just saying, hey, notice that this is not a subgroup. And here I'm pointing out why it's not a subgroup. Excellent. Let's see here. Consider the set, let's call it 3Z. You'll see this referenced in your book as well, which is the set of elements 3 times n such that n is an integer as well. So it's all of the multiples of 3. So if I consider all of the multiples of 3, and I do so under addition, then I'm still getting 0. And if I have, let's see here, 5 times 3 is 15. Well, I can also choose a -5 times 3, or 3 times -5, of course, 5 times 3, to get my -15. And 15 plus a -15 gives me 0. So I have identity, 0. I have inverses, just choose a negative n for whichever thing I ended up with. That's sort of a situation there. So associativity is inherited from the fact that Z is a group, so there's no issue there. I have identity, I have inverse, and of course, if I were to, I can verify closure here. Let A and B belong to 3Z, then A is equal to 3n and B is equal to 3m for some m and n that are integers according to our definition of the set. And let's see here, A plus B is 3n plus 3m. And of course, I can then recognize this as 3 times n plus m, because I have the wonderful characteristics of commutativity. If I didn't have commutativity, I wouldn't have this distributive property. Okay, you got to be really careful about that. But once I have that, then 3n plus m is in 3z, since n plus m is an integer, right? So I can write it as 3 times an integer. So I have closure. Plus 3z is closed. So I get this idea of a subgroup, right? I'm going to, we've talked about how I have the identity. We talked about how I have inverses. I told you that we get associativity inherited from the original group itself, Z, and then here I've demonstrated closure. So I know that I have everything that I need for a subgroup, and this is fantastic. So this is what we get for a subgroup. This is the idea, okay? A subset that is also a group. So let's take a look at a little bit more details on subgroups in our next video. So I'll see you back here in the office in just a moment.